Hello, I am Seo Seok. I am the first-year master's student in Terra Lab with Joungho Kim as advising professor. And today I will introduce my term project titled ChatGPT-collaborated imitation learning-based channel optimization of hybrid bonding through silicon via for high bandwidth memory. So here are the contents. I'll briefly introduce about the concepts and then propose my idea, verify my idea, and then discuss and conclude the presentation. So first of all, I'll introduce ChatGPT and why we need GPU module. So ChatGPT is a large language model serviced by OpenAI, and this GPT here refers to Generative Pre-trained Transformer. ChatGPT's raw data is fetched from the text-based database from the internet, shown on the left. And with this database, over 10,800 GPUs are used to train this ChatGPT, which has about 175 billion parameters. So the performance of this ChatGPT hardly relies on this the performance of GPUs. But these GPU models require higher and higher bandwidth because the number of parameters in the AI model increases about 10 times a year. And these large AI models need large capacity, so better memory module is required to efficiently utilize the AI model. So in the past, we needed to make a faster processor, which I referred to a car. But now our cars are really fast, but our roads are really narrow. So we have to make a wider road to make efficient GPUs. So due to these problems, GPU HBM module was introduced. GPU and HBM module can support fast and vast amount of data transfer between processor and memory. And this is possible because GPU and HBM is on the same package using silicon interposer. And these silicon interposers have shorter channels between DRAM and HBM and GPU, and fine pitch 1024 IO channels, which enhances bandwidth. Also, the HBM part, which is on the left, this part, the DRAM die is stacked with 3D, which it makes a smaller form factor with higher memory capacity. However, these HBM modules are getting to limitation because we have a height limitation in package, which is 720 micrometer, but we need to increase the HBM stacks due to the higher required memory. So, and the major bottleneck of this part is the bump size, which is here. So the bump size, it's limited. It's about we are using micro bumps right now. It's limited to about 20 to 30 micrometers, but if we want to stack more and more DRAM stacks, we need to decrease them. So, but using our current technology, various process issues occur. So this is a clear limitation that we should solve. So now I'll introduce the hybrid bonding TSV. So the left part is the micro bump that I briefly mentioned in the slide before. Its pitch is about 30 microns and gap height is about 15 to 20 microns, which limits the stack numbers. But on the right, there's hybrid bonding TSV, which has a less pitch and less gap height, about less than 2 microns, which then we can have a narrow gap, and narrow gap leads to higher stacks, which leads to high performance and low power consumption due to a shorter interconnect. So hybrid bonding, according to research, provides about 3 times energy efficiency, 15 times interconnect density, and better signal integrity compared to conventional HBMs, while still maintaining the same height of the HBM. But when we are designing these hybrid bonding TSV, we have to consider something. We have to consider signal integrity because they are a big issue these days. Hybrid bonding enables smaller pitch and additional stacks, and smaller pitch induces more crosstalk between interconnections because they're closer to each other. And if we have more stacks, we have more number of loading capacitance, which also leads to signal integrity issues. So when we are designing these TSVs in HBM, we have to carefully analyze signal integrity. And when we are analyzing signal integrity, eye diagram is the most important thing. So eye diagram is the ultimate indicator of signal integrity because it represents various signal integrity issues such as reflection, jitter, crosstalk, and etc. And how we obtain this eye diagram is by obtaining we input digital signals, and then we superposition them, and we get the eye diagram. And this opening here is what we are trying to see. So analyzing this eye diagram is essential to solve signal integrity issues over a broadband frequency. Yeah. But so we now know that eye diagram is very important in designing TSVs, but these eye diagrams have a major problem, which is the simulation cost. So there are many parameters in designing TSV. As we can see, these are just not even all, these are just some. We have 6 possible, very simple TSV parameter designs. And when we are trying to achieve the eye diagram, we have to follow these steps from design to 3. We first design the TSV, and then we put it into 3D EM simulation, and then we have to do a circuit simulation with ADS. And every time we change a single parameter, we have to do the whole process again. We have to iterate again. And this process is very time costly and high computing cost, because if we are just checking three values per one parameter, if you think about it, it's a lot of time. So we need a better solution to obtain the eye diagram, which is so essential for designing the TSVs. So first of all, we are going to use a scalable model of TSV to reduce simulation cost. So scalable model gets rid of the 3D EM simulation, 3D EM part. So if you look here, we have to design and then 3D simulate and then circuit simulate. But for 3D, for scalable model, we're getting rid of the 3D simulation part. So we have this design parameters, we change it into circuit parameters, which is a lot more simpler than the 3D simulation part. So, and we give the values, and this is done by previous research. So we eliminate the need of running a 3D EM simulator. However, running the scalable model even takes too much time for efficient design of HBM. So I thought about a new method, which is using machine learning. So as I said, 3D sim, and then what is it, circuit sim, but we can all make this process as one machine learning model using deep neural network. So if we use the deep neural network, we can just put in the design parameters, that's the 6 design parameters that I shown, and then put it into a DNN, and then just get the output, which is the eye diagram, eye opening area in this case. Yeah. So this is the main idea that I'm proposing. And previous work, which I did in the midterm of the last term project, was simply obtaining the eye opening of when we have a certain input of a TSV. So eye diagram is estimated by the ChatGPT-collaborated DNN model, and the raw data for the DNN model, which is the training data, is generated with various TSV design parameters, changing these parameters, and then estimation of my output was eye height and eye weight. And this can be done by inference of DNN model, which is more efficient than simulation-based conventional model. So these are my verification results, and I'll just briefly go over them. The model was created with 100 trained data, and my results just had about 5% error rate, and then my results became better with more trained data. So I can conclude that my DNN model is almost not perfect, but almost good as the ADS, the real data. But the limitation of my midterm is that our ultimate goal is optimizing the TSV channel. However, our previous model merely estimates the value when the design parameter is set. So, but our real objective is finding the optimal parameter that gives the biggest eye height and eye width when we give the range of design parameters. So this is like we need like a one step more in this situation. So to solve this problem, we need to introduce deep reinforcement learning, which is 강화학습 in Korean. So in deep reinforcement learning, the agent can learn without supervising through interaction with the environment. And by training the policy network, we can find the optimized policy that maximizes the reward. And when the state changes, the environment gives the reward obtained from the changed state and then updates the agent. And iteration of this project will make a good agent here, and then after that we can get a optimized design parameters in large and continuous spaces. However, this DRL method still have a limitation. As seen before, the deep reinforcement learning requires huge amount of interactions between environment to learn an effective policy. So if we have some few bad steps at the start, we can have very poor efficiency and poor exploration at early stages. And interaction between a DNN and reinforcement learning algorithm can result to issues such as vanishing gradient on the left. That will make the learning process very unstable. They will not converge. And also deep reinforcement learning requires complex reward function design, which is a big problem. So my idea was using imitation learning with random search. And I used, imitation learning is kind of a, it's not really deep reinforcement learning, but it kind of has it's in like a middle. Imitation learning is a supervised learning method. It's not unsupervised, it's a supervised learning method, which the expert collects data through interaction with the environment, and the agent is trained based on the expert. So we have two steps in imitation learning, which is exploration and exploitation. So exploration is where the expert gathers the data to collect the state, reward, and action. And exploitation stage exploits the expert data by creating a DNN model, which is a supervised process. And if you see in the previous page, I said IL with random search. So I'll explain random search, and I kind of briefly compare with grid search in this slide. So random search can explore a wide range of parameters with great efficiency. And also random search, we can have parallel processing, and random search can find optimal solution even with presence of noise. So if you see with the comparison with grid search, our optimal point is here, but if you just have a grid search, we can't find the optimal point. And I can't say random search has the best performance, but random search has great efficiency while training the data. So, and our key is efficiency, not accuracy here. So I chose random search as a method to explore the data. And I'll also compare random search to Bayesian optimization method, which is a very renowned method. So what Bayesian optimization does is that it targets to find the optimal solution by finding the next useful input that will maximize the objective function, which is the eye opening in our case. So if you were here, our goal is to get to here, and the model keeps trying to go to that place after iteration and iteration. But as you can guess, because it has multiple iteration after running this ADS module, the time complexity is it's a lot worse than random search with big O to n to the cubed. And also results of Bayesian optimization can end up in local minima instead of global minima. I'm guessing you guys seen a lot of this kind of picture. So if we are here, we have to go to the, let's say we have to go to the smallest part, but we end up falling here instead of here, which is the real optimal value. And while using this imitation learning method, I was collaborating with ChatGPT. So of the 3 steps that I shortened in the previous slides, ChatGPT can help me learn the basic concepts of the signal integrity, power integrity, TSV, hybrid bonding, all those concepts. And also ChatGPT helps us code the machine learning model, which was not easy for myself because I was not really a software guy in my undergrad career. So ChatGPT made every process a lot more easier for me. So my motivation and objective of our term project is due to increased requirement of performance gap between GPU and DRAM, higher bandwidth is required. And higher bandwidth leads to the requirement of additional HBM stacks, which creates various signal integrity issues. And to solve these signal integrity issues, we need to simulate TSV models, and these takes too much time cost. So to solve this, I propose a ChatGPT-collaborated imitation learning-based model for fast TSV channel optimization, and verify my proposed method and apply my proposed method to SIPI analysis and hybrid bonding TSV in the future. So this is my proposal. So this is the imitation learning-based TSV channel optimization for HBM. This is the whole picture. So I have a TSV pitch as an input, and I train the agent using imitation learning. And when the agent is fully trained, this agent will give the output, which is the optimal TSV diameter and TSV height. So this expert here is trained with the random search. So when I give a set input parameter pitch with random search, randomly the algorithm selects the diameter and height, and the diameter, and with that data, out of those lot of data, I choose the best data for the pitch. I choose the best data, which is the largest eye opening for a certain pitch, and then I train them into the agent. So that's like the very main idea. And our policy is updated by using mean squared error evaluation. So I'll explain in more detail in the later slides. So this is the overview. As I said, this is the initial state of our TSV. So I have a pitch that I set. It's a given pitch, and using random search, I select the parameters, other parameters such as diameter and height, as shown here. So then this D and H is chosen by random search. Of course, it's not completely random. It's within a certain range that I set using reference from the other papers. And then using these 3 data and every other parameters are fixed. I use the reward simulator, which is ADS, and then I get the eye opening, and then I get the data, and then these data goes to X, and I get the highest eye opening data for each pitch, and then I put it into the DNN training data, which is the exploration part. So yeah, I explained it in previous slide, but so initially our state as pitch and diameter, which is not set, and height not set, but with the random search we set the state, and then using ADS we get the eye opening, and then these eye opening makes a training data, and these training data yeah. So with the obtained state, the eye opening is obtained by ADS, and this is the exploration part. Exploration stage, as seen here, we have 2 stages. So exploration state is basically just random searching diameter and height, and then getting the eye opening with the ADS tool. And now this is the exploitation stage, which is more like a little deep learning. So as a data, I have 16 fixed pitches, and I random search 25 diameter and height set. So I had total of 400 data. And as I said before, I am choosing the eye opening that has the largest, I am choosing the diameter and height set with the largest eye opening for each given pitch, which is 16, because I'm choosing the largest among this 25. And with just 16 data, I am putting this in 16 data as a training set as an agent in DNN model. And this is called imitation learning because so what this does is that this DNN model imitates the expert. So expert is like it's kind of a tutor. So this agent DNN model cannot really have the performance of an expert because it was based on this expert, so it can't really have the performance of this expert, but it's like a tutor and student relationship. So just, of course, it will take a lot more time to become an expert. So the student, which is the agent, kind of gets until some level as expert, not perfect, but it's, of course, it's a lot faster. So that's why we're using it. So this is the brief process of DNN model, but I guess the professor explained it, so I will just go over it. And to explain the collaboration with ChatGPT, I kind of briefly showed what role we had. So as a human, myself, I generated the raw data output with input parameter with the ADS tool and made the CSV file with the data and selected the test input, which is the fixed with test input is the pitch of TSV. And ChatGPT, when I asked to program the imitation learning model, it chose the hyperparameters, programmed the DNN models, programmed the DNN models, chose the hyperparameters, and produced output with the test input. So as a whole, we made a ChatGPT collaborated imitation learning DNN agent, and which is based on random search based expert training set of data. So this is the brief dialogue that I made, that how I interacted with the ChatGPT. So first, our imitation learning model, as I said, it divided into exploration and exploitation. And the major part of exploration is a random search code. And I asked the random search code, the ChatGPT gave the random search code with the source code. And then after running the ADS myself with the random search data, I now have to exploit those data. So I asked him to filter the data with the largest eye-opening row, and then create a DNN model that has pitch as an input and diameter height as an output. And I told him what loss function I wanted to use. And ChatGPT gave me the source code, and he already chose all the hyperparameters, which needed a little tuning, but it was good to use. So this is the brief picture. So the input setting, the input setting is like this, and then the optimizer model, this is the neural network here, and then this is output, and this is iteration and output, and then I got the output. So to verify my model, if this is actually a plausible thing or not. So first thing is data generation for exploration. So as I said, we have roughly about 6 parameters in TSV, but I put the copper pad diameter, copper height, and insulator thickness as a fixed parameter, and as a design parameter. And I set three as a design parameters, which is pitch, diameter, and height of a TSV. And pitch, we have 16, as I previously mentioned, from 10 to 25 microns in 1 micron step. And for diameter, I have 6, and then height is from 40 to 60. And to generate the eye diagram, I have to do an eye diagram simulation for the raw data generation. So and to do this, I use the 8 stacked TSV channel, which refers to 8 HBM stacks, and I follow the HBM2 spec. So I use 1.1 volt as a V input voltage. Data rate is 8 gigabit per second, and the rising time is 10%. And I assume that loading capacitances exist between every DRAM stack, which is 0.2 picofarads here. And the hyperparameters that I use for exploitation agent for imitation learning is like this. I use 64 layer and 32 layer, and then add-on optimizer with ReLU activation function. And so this is my verification results of imitation learning based TSV channel optimization for HBM. So it's a little hard to see, but the table above is the eye-opening comparison between the random searched values of diameter and height and the output of imitation learning under fixed TSV pitch. So this 100, this number means that I ran the data for 50 times. So basically, this data is the best eye-opening from 100 times of random search at pitch 10.5. So obviously, this data has to be same or bigger than this data, because this is the best data from 50 sets, and this is the best data from 100 sets. So, and then these data is it's like the same. This is the eye-opening from 1 imitation learning, and this is the eye-opening from 2 imitation learning. So with the same logic, this number has to be bigger or same than this row. So I put it in red. So 6 of the 14, we have 14 test pitches here. So 6 of the 14 test pitches showed a better result compared to random search. And this imitation learning model was only trained on a lot less data. So the optimization speed vastly increased. So this imitation learning model was learned based on random search, but with the less number of random search, it gave a better performance compared to 100 random searches. So imitation learning actually is a pretty good, pretty efficient tool compared to the random search. In this, we can conclude that it's a better random search tool. And this is our graph of results. So on the left, I compare our imitation learning model, with reinforcement learning. So reinforcement learning, as I said before, has a problem with converging and speed. So its loss function is not decreasing a lot. But imitation learning, when we use it, it decreases very fast, and we just doesn't need a lot of iteration. And the graph on the right is showing that our imitation learning results shows better results than average of 61 random search. So, and the second, if we run the imitation learning the second time, because imitation learning result gives a little different data every time. When we run it the second time, we get the better results than average of 71 random search. So the imitation learning was trained based on random search. So it doesn't beat the performance of random search every time, but it greatly reduces the time cost. And I forgot to mention that this imitation learning method, when we get the diameter and height, I run it in the real ADS, so it's a real data. So it's not like a estimated data. So it is a plausible conclusion. And now I will discuss about ChatGPT philosophy that I collaborated using while using imitation learning. So I included 6 key abilities of research, which includes predictability, explainability, reproducibility, repeatability, and flexibility and novelty. And I'll just go over one by one. So predictability, the ChatGPT can predict certain phenomena very well, which is based on their database, which is similar to human. Then explainability is ChatGPT can explain complex concepts, and I actually think ChatGPT does better than us because it can have it can target various users. And reproducibility, which is essential in research, it's not really good. ChatGPT is not really good at it because it gives a different answer even when the question is exactly the same. And repeatability is ChatGPT is better than human because ChatGPT is a fast worker and it does not get tired while processing. So this is different compared to human, which we really need rest sometimes. And flexibility, which is a little connected to reproducibility here. So ChatGPT gives a different answer every time. So in other words, it's kind of flexible. So human kind of tends to get biased to certain solutions because they have a limited knowledge. But since ChatGPT has a little more knowledge than most of the human, it's not really biased to certain solutions. But when we're talking about novelty, ChatGPT is trained based on human data, so it doesn't really have any groundbreaking ideas. So ChatGPT cannot really create completely new ideas that may change the world. So there is still some space for humans. And we are predicting about the human work processes using ChatGPT. As we already know, there exists many more generative AI models that has powerful features such as Google Bard, DALL-E, Meta, Llama from Meta, and ChatGPT. And a lot of these big tech companies are competitively diving into generative AI market, and all these generative AI has unique strengths. So generative AI is like a cloud brain of human, so we can use it anytime, anywhere, and we don't really have to memorize everything anymore. So we have to use them smarter. So smarter usage of generative AI models will be essential to enhance efficiency. And so I kind of made an analogy with my imitation learning and ChatGPT. So my imitation learning, the agent learned from the expert using imitation learning, and I thought our future is similar to this. So there's massive database on the internet. ChatGPT kind of filters them, trains them, and it becomes the expert. And using ChatGPT, we can learn from those experts, which is of course, I mean, reading the textbook and thoroughly is better to fully know something, but we don't have time for that. So we can use the expert and greatly reduce time, but get to a certain level. So if we use the generative AI models, it's easy to get to those certain level of knowledge. So, and the key we'll be choosing, as mentioned in previous slide, is the key here is to choose which generative AI model, which expert to exploit the model. So my major contribution goes ChatGPT-collaborated imitation learning method, TSV channel optimization method, is proposed to reduce the cost of complex process of conventional method of designing, and proposed the first ChatGPT-collaborated neural network TSV channel optimization, which is achieved with limited human programming. And also this proposed method is not limited to specific channel situation, which is good for general purposes. And in conclusion, in order to improve signal integrity performance, TSV design is essential in next generation HBM. And also conventional TSV design method requires too much simulation cost. So the proposed method using ChatGPT-collaborated DNN model can design hybrid bonding TSV with less time and cost efficiency. And proposed method will improve performance and can be applied to other application in which hybrid bonding TSV is applied. Thank you.